Javier.
Okay, so thank you everybody for joining us. This is our 11th seminar of the REACH seminar series, if I am not wrong. Today we have the honor of receiving Mathilde Cannat. She's going to be talking about the spreading modes and ultra slow spreading mid-ocean ridges. And I don't know if I need to present her. I think she's extremely well known by the community. I'll just mention that Mathilde Cannat started working on ophiolites during her thesis work in the University of Nantes. After that, she did a postdoc in the University of Durham, and then back in France, she joined CNRS, first at Brest, then she came to Paris to the UPMC, the University of Paris, Pierre and Marie Curie, where she has, and then she joined she was at the base of creating the Marine Geosciences group at IPGP, where she has been since. And in terms of recognition, I will just mention that both nationally and internationally, she's been recognized. First in 2009, she received the silver medal of CNRS. It's a prestigious distinction here in France. She became in 2014 AGU fellow, and last year she received the Stephen Muller Medal from the European Geophysical Union. So I'll leave it at that, and I will leave the screen more than the floor to Mathilde. Thanks.
Okay, thank you, Javier. Thank you for inviting me. And the original title was to talk about modes of ultra slow spreading at the Southwest Indian Ridge, and how actual tectonics adjust to varying melt supply. And I choose to give it a broader scope, and the new title would be like spreading modes at slow and ultra slow spreading mid-oceanic ridges. But I'm still going to be talking a lot about Southwest Indian Ridge, and also about how actual tectonics and melt supply kind of play together. And by spreading mode, I can say that what I mean by spreading mode is really the combination of all the processes, the mid-oceanic ridge tectonic, magmatic, and hydrothermal processes that together determine the composition and the structure of the oceanic lithosphere. And I'm actually not going to talk so much about these processes, nor about the composition and the structure, but I really want to focus on how the melt supply affects these. And the results and the ideas come from working with a bunch of people, and most notably with the people cited here, and I'm not going to read all the names, but okay, and oops. Okay, so the organization of the talk, I will first have 3 slides of introduction of what I'm going to talk about, really, how I take this topic. And then I will talk about spreading modes at the low melt supply settings, at low melt supply settings at the mid-Atlantic ridge. And then I will talk about spreading modes at very low melt supply settings at the Southwest Indian Ridge. And then the rest of the talk, I will go back to more magmatically active or robust settings. And first I will talk about the transition from low to higher melt supply, because there are, of course, also rather high melt supply settings at both the Southwest Indian and the Mid-Atlantic ridges. And then I will talk about very recent ongoing work on modeling the actual thermal regime at slow and ultra slow spreading ridges as a function of melt supply, and try to show you how these modeling results may translate in terms of the geology and the spreading modes. So the first introductory slide is one that talks about the discovery that slow spreading ridges are segmented, and that they are segmented with respect to their melt supply. So here is written that gravity surveys confirmed by seismic surveys, and I give you the earliest reference, show that crustal thickness at the slow spreading mid-Atlantic ridge is variable at scales of a few tenths of kilometers, indicating variable melt supply and suggesting an equally variable actual thermal structure. So that's the observation with the bathymetry that is segmented with deeper end of segments and shallower middle of segments. And that corresponds to a segmentation of the gravity signature with a more negative anomalies at the center of the segments. And the interpretation would be that, okay, so you see the crustal thickness varying, and it's inferred that there is some mechanism in the metal that it is able to bring melts and more melt towards the center in this particular interpretation. But what you see is that these dashed lines are inferred isotherms. So already there is this notion that you have segment centers where you have the crust and a rather hot thermal regime, and the segment ends where the crust is thinner and the thermal regime is colder. And the second thing that is really necessary to know to understand the rest is that this idea that there is a segmentation of that the thermal structure leads to places along the ridge, the slow spreading ridges where the lithosphere, the seismogenic lithosphere is thicker than the crust, comes from microseismicity experiments that have shown for many years. The earliest experiments were in the 1980s, actually, that the seismogenic part of the mid-Atlantic ridge actual lithosphere is at least 5 to 8 kilometers thick and is thicker than the crust at segment ends. So that's two cross sections, one at the segment end and one at the segment center. So here at the segment center, you see the gravity-derived crust is the seismogenic part of the lithosphere is contained within the crust, but that's not the case at the segment end here, where you have earthquakes in the mantle. And the consequence of that is, in terms of the spreading modes, really, is that if the actual lithosphere is thick, the magma is not happy at shallow depth, and it cannot form long-lasting magma chambers at crustal depth, and it will form discrete intrusions instead. And the thing that goes together with that is if the brittle plate on axis is thicker than the cumulated melt column, then in order to separate the plates, you need to actually cut into the actual plate, and therefore you need to have faults that get into the mantle. And if you get normal faults into the mantle, then peridotites will be faulted up, and the crust will be composite. So that's one evidence of that is the discovery of rather evolved gabbroid diclets in actual peridotites. And we can see that it can be shown that these diclets were included in peridotite that was not that was already cooled into the lithosphere, and then this is the sketch possibly of the segment center with the crust and the lithosphere having kind of the same thickness, and at the segment end you've got a thicker plate than you can fill with the melt, and that brings you to the necessity of having some faults getting peridotites up. That was the crude sketch of what the fault could look like made at that time. So now I'm going into the talk really. And since then, of course, there has been a lot discovered about the modes. I would say particularly about the modes of spreading at segment ends, the modes that as was soon discovered, or not that soon actually, a few years later was discovered that these faults that bring peridotites into the crustal levels are actually very large offset faults that can have offsets of 10 to 20 kilometers, and that are called detachments. And it was also shown that these faults along the mid-Atlantic ridge, they have very 3D geometries. Their offset is of the same order of magnitude as their extent along axis. And here's a very nice reflectivity image of one of these faults with the striations parallel to the movement. And this is the picture of the discovery of the this type of faults by Joe Kahn and collaborator. And again, microseismicity is really important to understand what's going on, because thanks to the distribution of microseismicity at the few examples of presently active detachment faults, we can say for sure that the fault at depth is very steep, at least 70 degrees. And therefore, because the fault emerges at very low angle, it means that there is a very large flexure of the footwall up to 70 degrees. And the other thing that the seismicity tells us is that the seismogenic part of the lithosphere, which could correspond thermally to 600 or 700 degrees, less than 600 or 700 degrees, is at least 12 kilometers thick. So it's definitely thicker than the crust. And another thing that is important for these mid-Atlantic ridge detachments, and that's why I call them low melt supply and not amagmatic, is that there are actually a lot of gabbros intruded in the peridotite as they are exhumed. And so gabbros form veins and kilometer-sized bodies in the footwall peridotites. And here I have a little asterisk saying that if you look at statistics from dredging of several of these footwalls, you find that it's in the order of 30–35%. And also these gabbroic bodies are constructed by 100-meter scale successive syntectonic injections. And that's things that were learned from numerous ODP and IODP drilling. And also, and that's what I'm showing from the interpretation of seismic tomography. So here is a work, a model of seismic velocity model for this corrugated detachment surface here. It's a long axis section, and it shows you that here you've got outcrops of peridotite, and here, just where it's corrugated, there was a drill hole, and it recovered only gabbros, and it corresponds to fast seismic velocities in the upper crust. And so using this proxy, it could be proposed that the gabbroic body is indeed a few kilometers across. And another thing that is important to know about this low melt supply mode, typical of the end of segments at the mid-Atlantic ridge, is that when you look at the rocks that are really deformed near in the exhumed fault surface, you find that, well, of course, that one thing that was learned is that strain weakening in the fault zone is really the key to form long offset normal faults and therefore actual detachments. But at these corrugated detachments, you've got, when you look at the highly sheared rocks, you see that they are either sheared gabbros or they are, as shown here, altered gabbroic peridotite mixture. So here the gray-green is altered gabbro that has been transformed into a mixture of chlorite and amphibole. And the orange clasts are clasts of the peridotite. And here another example is, so that's really a former melt injected peridotite that has been sheared. This one is different. It was a serpentinite, and the serpentine was broken up, so there was a brittle event. And in the fractures, you had a fluid that was enriched in silica and replaced the serpentine by talc. And then in the talc, you see these very continuous shear zones that really can do a lot of strain. And that's a view of the upper surface, the exhumed fault surface at the Atlantis massif corrugated surface. Okay, so now we're going to very, very low melt supply. And for that, we move to the Southwest Indian Ridge. And to a very specific place of the Southwest Indian Ridge, because actually a lot of the Southwest Indian Ridge has a melt supply that is, with respect to spreading rates, comparable to other slow ridges. But this particular place has probably a very colder mantle than elsewhere. And it's a 600 kilometers long part of the ridge next to the Rodriguez triple junction. And when you look at the average crustal thickness in this region, it's about half normal. And what's more, this low melt supply is focused to three big volcanoes. There are number 8, 11, and 14 in this cross section. And so the intervening segments or parts of the axis are even more poor. And so it is a melt poor, I mean. So that's, it is a natural laboratory to document the effect of varying melt supply from near zero to enough for a 7 kilometers thick magmatic crust at the level of the actual volcanoes. And when we look at so before I was showing you the bathymetry of this large region, now I'm showing you the bathymetry also, but just it's shaded and it's categorized with different types of seafloor morphology. Here you've got very clear spreading perpendicular. The spreading is north-south. Spreading perpendicular scarps, and we can't see them at this enlargement, but there are also volcanic cones, so that's called volcanic seafloor. And then in white, I've traced the limits of the corrugated surfaces. In some, you can see the corrugation. And then there is this, this seafloor here that is neither volcanic nor corrugated, and we called it smooth. And we called it even smooth because very often when you look at it, you see that if you look at the opposite plates at the same time, it's the same type of seafloor morphology. And we can use the gravity anomaly as before as a proxy for crustal thickness and melt supply. And if we do that for this entire region, looking at the average gravity signature of the smooth seafloor in places where it faces smooth seafloor on the other plate, and then the same thing where it faces volcanic seafloor on the other plate. The corrugated seafloor always faces volcanic seafloor on the other plate, so the average is here, and the volcanic seafloor faces volcanic. And so we see a decrease in the gravity anomaly that can be interpreted in, and that's confirmed by limited seismic data that we have in the area. It can be translated into increasing crustal thickness and melt supply. Okay, so now I'm going to spend a little time to describe this smooth seafloor spreading mode. The first thing is that it is really nearly amagmatic. There are a few hills of hummocks, of basaltic hummocks, but they are sitting on a seafloor that is, here it's a reflectivity image in this area. That's a view on the actual valley just at that place. And when you dredge this less reflective seafloor, you get 97% serpentinized peridotite with only 3% gabbros and basalts. So it's really almost completely amagmatic. And when we look at the bathymetric map and try to trace, to interpret the formation of this seafloor, well, the first thing is that we've got to find a mean to get peridotite exhumed on both plates for a long time. So that's the present day ridge axis, and that I think is anomaly 5, so that's 10 million years. And so the interpretation we made, and it's being slowly confirmed by more data in recent years, is that we had a flip-flop type detachment model with the present day detachment here is actually offsetting the exhumed footwall of the previous detachments that's there, which itself offset the exhumed footwall of the one before, etc., etc. And if we then interpret the top of the blocks as the trace of the breakaway, which erosion kind of left there is some erosion, so the top of the block is not really the breakaway, but at that scale it is. And we can see that this is not 3D at all, like the corrugated surfaces. It's really very linear faults that can extend up to 90 kilometers for the longest one. And that actually, they extend all the way through the amagmatic corridor. And depending on the time at previous times, the volcanic seafloor can extend and eat a little bit into the amagmatic corridors. Okay, and so now we have some seismic data on this smooth seafloor situation, at least in the actual region, and we find so that's a view of that's the same view, and this one I like it because you're looking down from the footwall of the exhumed by the present day detachment, and you're looking down towards the south, and you see very well these poorly reflective, quite sedimented peridotite with basalt hummocks on top. And in this region, so this section is here, this is the footwall. We see that the seismic tomography indicates that we do have a crust. So it's even quite thick in this region, up to 5 kilometers. And of course, we interpret it as mostly made of serpentinized peridotite. But there are also quite a few reflectors. Some reflectors, like these ones, are clearly related to the active fault. And if you look at their dip, they're dipping about 50 degrees in this region. And the exhumed part of the fault, I won't show you seafloor geology in this talk, but the fault is exhumed at dips of about 30 degrees or less. And so we also have north dipping reflectors, which we interpret as conjugate very small offset faults that are related to the detachment. And there are also a number of subhorizontal and kind of complex reflectors that we think are related to the emplacement of magma, because what can produce a contrast enough to make a reflection in a serpentinized crust is you have to either invoke tectonic damage, localized melt injection, or contrast in the degree of serpentinization, or all three causes. Okay, and one thing that is important to understand about this this spreading mode is that it takes a very long time and it's protracted to build the new lithosphere, because before the lithosphere is finished, if you want, and moves in one plate or the other, it can take up to 3 million years. And the story is two-phase. With first you exhume the footwall of the older detachment. So in our case, that would be dn+1, like for example D2. So presently and then you take the part of this exhumed footwall and you put it into the hanging wall position of the next detachment. And in this hanging wall position, it is faulted, and it is also intruded by some basalt, not much, but a little bit. And so it's a very specific. It's very different from the asymmetric detachment that we see in corrugated context. Okay, and that's not published yet, but we do have some information on the seismogenic lithosphere thickness beneath the smooth seafloor, and it's actually not that much thicker than for corrugated detachments in the Atlantic. It's you can see that here you've got dashed lines that are 5 by 5 kilometers relative to the seafloor, and you see that the deepest earthquakes recorded are at depth of about 15 kilometers. Okay, and in terms of the strain localization, that's very different from the corrugated detachments, because what we find is that everything, there is no or hardly any role for melt products. Everything goes into deforming the polydotites. And so in green schistous conditions and in places where you have water, you form serpentine, and then typically you will find rocks like these ones that are heavily brachiated. But when you look in detail, it's a mixture of brittle deformation that forms clasts of serpentine, and then the clasts are recrystallized, and here you have a nice example of a chrysotile that forms kinematically as the rock is deformed. And if you are too deep or too hot to form serpentine, then what you do is you do very intense and viscous deformation of the polyidotite with a recrystallization of olivine in very fine grains that are indicative of high stress conditions, and the temperatures of this deformation are between 800 and 1000 degrees. And I'm not going to show you the numerical modeling, but in short, when you try to form the flip-flop detachments in this thick lithosphere without having this mechanism for strain softening that comes from grain size reduction in non-serpentinized polyidotite, that's represented in red here. If you don't involve this mechanism, you don't succeed. But if you do, then you can reproduce the flip-flop succession with a regularity that is very similar to the one we observe in the field. So that's okay. So now I move to the last part of the talk. So we are moving from very hardly any magma to more magmatic systems, and along the same ridge and at the same spreading rate. And what I'm showing you here is a cartoon that's constructed with two a cross-axis actual profile. Profile 1 is here, so it's right in the middle of the smooth and amagmatic spreading mode. And profile 3 here is not exactly at the volcano, so the crust is not yet that thick, but it's the first profile that has a completely symmetrical, that is symmetrical, and shows no evidence for large offset faults, but rather for conjugate faults and also a lot of magmatism. And the cartoon shows that what we see is that there is absolutely no indication for any accommodation or any problem encountered by the system to go from having a detachment that roots at more than 15 kilometers depth into high stress deformed non-serpentinized polyidotite, to go from there to a symmetrical volcanic type of spreading within less than 30 kilometers and with no accommodation. So the concept is that really we are looking at the ridge axis. The actual domain is really a place where the faulting accommodates in real time and locally to the melt supply. And it probably accommodates in two ways. The first is that, of course, if you have more melt supply, you don't need to have so much displacement on your fault, but it's also that the melt is modifying the rheology of your lithosphere and giving you more opportunities for strain localization, etc. Okay, and if we look closely, so now I'm going to volcanic modes, volcanic spreading modes at low and ultra slow spreading ridges. So we're looking at this profile 3, and we have constraints on the crustal thickness. It's about it's actually about the same as in the smooth seafloor. It's about, but the crust is clearly more mostly magmatic. And the lithosphere, the seismogenic lithosphere is at least, oh, I missed the scale, but it's clearly thicker than the crust. And so we are in one of these situations where you could, if you want to separate the two plates, have the two plates separate, you need to have faults that go into the mantle. And that provides you with the opportunity to incorporate, probably not much, but a little bit of peridotite into the crust. And as a matter of fact, we've got a dredge here. It's even in a more magmatically robust part, closer to the volcano. We've got some peridotites out the outcrop along the fault here. And the other thing is, so that's the first thing we can say with this situation. And the other thing is that, and I'm showing, so in this cartoon, what we see is that we can predict that, of course, if we bring more melt is heat, so we are going to heat to thicken the crust, but we are also going to thin the lithosphere and have a hotter thermal regime. But it's also important, we can predict, to know where the melt goes, because it probably can pool happily at the base of the actual lithosphere. But if it does that, or if it's intruded into the lithosphere at levels that are not within the reach of the hydrothermal system, which is kind of schematically shown as the dashed line here, then the magma will cool slowly and provide a lot of heat. And so I'm describing this the other way around. But if you intrude deep, then the lower crust becomes hotter, the lithosphere becomes thinner, and of course it has impact on the tectonomagmatic processes. If you intrude shallower in the reach of the hydrothermal fluids, then you're going to basically extract all your heat, and your crust will be overall cooler with lots of tectonic consequences. And so the idea is that we can expect to have volcanic spreading modes at slow and ultra-slow ridges that are very diverse, and that are actually probably more diverse than the detachment dominated modes that I have described before, and will depend on the actual thermal regime and how much melt there is, and also where it is emplaced. And to look in details into that, we have started doing some thermal modeling that I'm going to show you. And one important constraint in this thermal modeling is the geophysical constraints we can have on high melt supply and member settings at slow and ultra slow ridges. And there are two very well studied and member settings in these type of slow ridges. One is the Lucky Strike segment with the Lucky Strike central volcano, where the magmatic crust is 7.5 kilometers thick. The actual metal, you have an actual melt length reflector at 3.5 to 4 kilometers. And if you have basaltic melt, it gives you a thermal constraint, because it tells you that probably you have a temperature of about 1000 degrees at this depth, and the spreading rate is 2.4. And the other really nice high melt supply and member setting is along the Southwestian Ridge further to the west. Spreading rate is the same as in the smooth seafloor area, but the crust at the segment center is 9.5 kilometers thick. And here also, there hasn't been a reflector, actual magma lens reflector detected, but there is definitely a very low velocity melt crystal mush below 4 kilometers. So kind of a comparable thermal regime. And so the idea is to use in these models is to use the modeling approach that was developed by a student of Jean-Arthur Olive in a recent paper. And these models are neat because the first thing they do is they do model the hydrothermal circulation in a kind of a realistic way, and the domain of hydrothermal circulation is controlled by the position of a cracking front that is actually calculated within the model. And then you can in place melt at the frequency that you want. So you can place melt in the shape of that you want also. So in the models that I will show you, the melt is injected as a 200 meters by 4 kilometers melt length, but you could adjust that. And you can also in place the new melt, each new melt injection, you can place it below below an isotherm of your choice. And that's a way to reproduce the emplacement of melt at deeper or shallower levels. And so in this example, the melt has been injected at intervals of 9,000 years. And if you integrate that at a spreading rate of 1.4 centimeters, that gives you a 6.3 kilometer thick crust. I'm sorry, I have I need to close the window because the kids are playing with crack. I don't know the name. So anyway, and the melt here in this cartoon is placed at the 1000 degrees isotherm, and what it shows is the position of the crust corresponding to this interval of injection, and then the position of the 1000 degrees isotherm, the position of the 650 isotherm, that could be the base of the seismogenic lithosphere, and this could be the base of the more viscous lithosphere, if you want. And what you see in this example is that clearly we are in a situation where you will have crystal melt mush in the lower crust, but you will also have a seismogenic lithosphere that can accommodate faults on most of the crust. So that may be a situation a little bit comparable to the geology of this profile I showed you. And so with these models, what we can do, and I'm showing you really preliminary results of Jie Shen's PhD work. The first example I show you is what happens if we explore the effect of varying the melt supply at a constant spreading rate. So in this case, and all the melt is placed below at the same level, if you want. And here, a very long interval between melt injection is equivalent to no melt. And we kind of tuned it so that it would fit with the smooth seafloor lithosphere thickness, more or less. And then if you start having a smaller interval between melt injection, you will get a situation in which clearly you've got a crust that is the same thickness as the seismogenic lithosphere, and therefore you're going to have a lot of faulting in your situation. And you also won't have much in the sense of a hydrothermal circulation because the gradient, the thermal boundary layer is very thick. So the hydrothermal system is not very efficient. And if you increase the melt supply, then you've got a thinner thermal boundary layer and hotter hydrothermal system. So that's one thing we can explore. The other thing is to explore the effect of varying the melt emplacement level at a constant melt supply. So that's really this question of whether the melt is, and you can see that if you emplace all the melt, as in this case, so that would be for 6.3 kilometers thick time integrated melt column, and so that's the and it's the same in all the diagrams. So if you inject all the melt at 650, you see that you have a very vigorous hydrothermal system, a very thin thermal boundary layer, but then you will have a thick lithosphere on axis because your 1000 degrees isotherm, it's going to be cold, but relatively rigid down to a great depth. And also you will have an inverted temperature situation with a perched kind of melt mush that will be transient. And if you place it all at the 1100 degrees isotherm, then you won't get much of hydrothermal cooling, and that helps you thin your lithosphere a lot, as we could predict. And we are also exploring models that are probably more geologically realistic, in which you inject simultaneously a part of the melt at different levels and have a different system. And the final example I show you is what happens if you look at if you explore what happened when you have a constant melt supply and you vary the melt and placement level, and this time for a very high melt supply and member, and you see that you have exactly the same melt supply in all the situations, but your thermal regime is really very different. And so if you imagine melt trying to crystallize as a gabbro in each of these settings, you can see that it's not going to be the same at all. And also if you imagine the hydrothermal system obviously is very vigorous here, is a bit less vigorous here, and almost non-existent here. And if you think in terms of faulting, it's also very different. And so that's what we are trying to do. And with that, I will leave you with 4 key points that I wanted to make. The first 3 I've made during the talk. The last one I will do as a conclusion. So the first one is that melt accommodates part of the plate divergence. That's for sure reducing the need for actual faulting, and that faulting modes in actual domain adjust locally to melt supply and lithosphere thickness. And the second is that if the actual lithosphere is thicker than the cumulated melt column, the mantle-derived peridotites are faulted up and the crust is composite. And it might be that it's not much composite, but you still have this potential of finding ultramafic rocks at the seafloor. And the third is that at a given ultra-slow spreading rate, the thermal state of the actual lithosphere, and therefore the spreading mode, really, because is sensitive to spatial 1 to 10 of kilometer, and to temporal changes in the depth and frequency of melt and placement. And the fourth point is that these temporal changes in the depth and frequency of melt and placement, they likely occur at scales that are smaller than the time it takes to fully accrete a new portion oceanic lithosphere at these slow, ultra-slow rates. If you look at the width of the actual valley at the mid-Atlantic ridge, you can see that in order to be completely finished, the lithosphere has to be at least 1 million years old. And it's very likely that as can be observed in other volcanic systems, the frequency and the changes in melt and placement occur at much smaller timescales. And the consequence is that we can predict that there should be a large diversity in the composition and structure of slow and ultra-slow spread oceanic lithosphere, because to build one particular column of lithosphere, you have a chance of going through a range, possibly not from detachment dominated to volcanic, but within the volcanic realm, you have a chance of going through a lot of situations where you've got your lower crust hot or your lower crust cooled, and your hydrothermal system cooling your magma very fast, or etc., etc. So that's my point. Thank you. Thank you.